Hi everyone, this is Jake Fry, and today I'm going to talk about motion in one dimension. And for this video, everything is going to be in general, so it'll be later videos that I use the equations that I show here in order to do examples. Alright, so now that we have all the tools needed to describe motion from the previous videos on my channel, we can proceed through many of the commonly seen cases. And each time, we will increase the complexity of the problem. And so in this video, I will focus on the simplest case, where it's motion just in one dimension and with constant acceleration. Alright, so for vectors, even with motion in 1D, we will continue to use the vector quantities position, velocity, and acceleration, but they will only have one component. And so you might be wondering, well, how can something with just a single component be a vector, which means have both magnitude and direction? Like, where's this direction all coming from? So for an example, you can think about the position vector, and it would lie upon a number line instead of, coordinate axes in 2 dimensions. And so a number line has points both in the positive x direction or in the negative x direction. And so that gives you your directionality that's required when you have a vector. And so you might think, oh, okay, so if it just has one component, it might be all the problems are super simple to solve. And so that is definitely not true. And this is because the parameter time can be used to create a very complicated functional form for each of the vector quantities, even in a single dimension. So for example, if you have a velocity that is something like the velocity as a function of time, even though it's only along the x direction, the magnitude could be something like, t cubed plus the natural log of t minus sine of t divided by the 8th root of t. And so that's a very complicated function to wrap your head around. And so, yeah, even though it's just a single dimension, lots of very interesting physics can still occur. Alright, so now we need to recall the relationship between each of the common vectors used to describe motion. And so you can see from on the right that all of these commonly named vectors are connected by either being the derivative or antiderivative of other commonly used vectors. And so if you have, say, the acceleration and you need to get the displacement, you would have to go back to the position using the integral twice. But we don't necessarily have to always use calculus to solve problems. So if you're in, say, an introduction to physics course that happens to be learning classical mechanics, instead you might be exposed to kinematic equations, which in this case would assume constant acceleration. And so these 4 equations are extremely common to see if you're trying to solve these motions in 1D problems. And so, yeah, trying to understand them and memorize them is usually what people are taught to do. But remember that you can always use calculus in order to derive each of these. So if you're on a test and you can't remember these 4 equations and you need to use them, you can always derive each of them from other equations, just remembering the relationship between each of the vectors. Alright, so let's just go through them. So for the first one, if we wanted to know what the final velocity is, given a constant acceleration, an initial velocity, and a time, it would be given like this. So the final velocity equals your initial velocity, v naught, plus your constant acceleration, a, times time. Cool. And then what if you wanted to know the displacement, but you don't know what the acceleration is, even though you know it's constant acceleration, but you happen to know the starting velocity and the end velocity. Alright, so all you would have to do in this case is take the average of the starting velocity, v naught, with the end velocity. So that would just be v final plus v naught divided by 2 multiplied by time. Cool. Alright, so then the next problem you might be able to see that it would end up being the integral of the first equation, which would make sense since the displacement delta x should be the integral of the velocity. But in case you don't see that, we can just look at the equation and have it memorized. And so it would be that the change in x equals the initial velocity v naught times time plus 1/2 of the constant acceleration a times t squared. Cool. All right, and then the last very commonly used equation is basically if you have what your initial velocity is, what your constant acceleration is, and how far you travel, but you say don't have a clock or a stopwatch, you can still figure out what the final velocity must be. And so it would be given by the final velocity squared equals the initial velocity squared plus 2 times the constant acceleration times the change in position. And so this equation might be a little bit harder to derive, but you can definitely do it from the other 3 equations. And so yeah, I guess in future videos, I will show quite a few examples on how to use these kinematic equations in 1D in order to solve some common problems. All right, thanks.